Everyone, so hope you had a good weekend, and we start again the second set of lectures. So the first set of lectures is on quantum chaos, and it's a great pleasure to have Arul Lakshminarayan from IIT Madras giving these lectures.
Thanks a lot, Abhishek, and I should especially thank Abhishek and Sanjib for giving me this opportunity to put together this set of lectures, which I haven't actually put together fully so far. So you can see lectures 1 to 3, so I have some homework to do. But okay, so already lectures 1 to 3 is a little bit fat. So we'll try to, I've given 1 to 3 because I know I just waffle around and don't convey as much as I probably should. So the aim of this set of lectures is going to be the following. It said, my agenda said quantum chaos, random matrix theory, and statistical physics, by which I interpreted the last part to be some of the things surrounding maybe eigenstate thermalization hypotheses, which connects quantum chaos, random matrix theory, and statistical physics, and has been a very active area of research and continues to be explored. So, but as a prelude, I thought we should have some classical chaos. So the prelude will probably occupy us today. But I hope to come to quantum chaos by tomorrow, and hopefully third day RMT, okay? But let's see how it goes. And by the way, please do feel free to stop me. We are in no hurry, okay? Because I have the notes, so I don't have to speak it. You can just read it. Okay, it disappeared, okay. Maybe I have to speak it after all. Yeah, okay. So I'm going to concentrate only on Hamiltonian systems, not dissipative. Okay. So roughly that's what I have on my board there. So first of all, some preliminaries, and then I'll introduce some very simple systems which are also chaotic. So these are 1.5 degrees of freedom systems, which you can, if you haven't already explored, you can do that very easily. And actually, it also leads to a very classic set of models, which people have studied over actually many decades now, and also been experimentally realized in many different contexts, both classical and quantum, these area-preserving maps. And so we'll talk a bit about that. Yeah, so 2 degrees of freedom Hamiltonian systems, which are the smallest you need to see this complexity, which we call chaos. And then I'll go on to general things such as the Poincare recurrence theorem, ergodicity, mixing, and the definition of chaos. And then I will treat some exactly solvable models of classical chaos, simplest models, but which are exactly solvable in the sense you can understand everything. There's no mystery left, the baker and the cat. So that's roughly the agenda for today. Tomorrow we'll talk about the quantum aspects of it. Okay, so let's see how we can go there. We have this cheerful clock ticking down. Abhishek is more or less accurate, right? Yeah. It's on. It's already 10 minutes above. Okay. All right, so classical chaos. So classical chaos, by that we mean deterministic systems, which means no stochastic input by way of noise or randomness is an input. It's completely deterministic, is determined by equations of motion. And for classical systems, these are just Hamilton's equations of motion. So we have in mind d degrees of freedom. So we have these position coordinates, d of them, or generalized coordinates, and their conjugate momenta. They constitute a phase space. It's a set of all points in this two-dimensional phase space. And That's our phase space. And every point on this is a point in phase space in this 2D dimensional space. And these points evolve according to Hamilton's equations of motion. These. So first of all, there is a Hamiltonian, which is a function of all of these. So it's just a one scalar function there. So QD, P1 to PD. So it's a remarkable Hamiltonian, it's a remarkable dynamical system in the sense that a single function is determining the flow of all these 2D dimensional variables in this 2D dimensional space. And therefore, it's a very constrained, a very special system, but nevertheless chosen by the laws of physics, and therefore very important. So if we start with some initial point there, Q0, P0, it's going to evolve according to Hamilton's equations of motion and go to some other point at a later time, Qt. So it goes to the point Qt, Pt at a later point. And all the chaos that we're talking about is inherent in this flow. Is not because of anything else. There's no randomness put in this Hamiltonian. There's nothing strange about it. So the fact that you can have complex motions in this kind of deterministic systems was known since the works of Poincare. In his study, famous study of the three-body problem, the gravitational three-body problem, when he realized that perturbation series do not converge due to what are called problems of resonances. Resonances kill these, make these series diverge. And he was the first one to have a glimpse of what we today simply call chaos in Hamiltonian systems. So it's the three-body, you know the famous Kepler problem solution. Of course, there are two gravitating objects, Newton's laws of gravity, and essentially the conic sections are solutions to this. Because of a lot of, it's a center-pose motion, and a lot of conserved quantities. But if you have a third object, like the Sun, Earth, Moon system, or actually the solar system has so many other objects, then this question is of the stability of such a system. And Poincare pointed out that actually these series don't converge. And today it is believed that the solar system is chaotic with a very small Lyapunov exponent. And Pluto, for example, is the most chaotic of the whole lot. It was also demoted from a planet fairly recently. It will leave the solar system probably in the range of millions of years. So the issue of stability of the solar system not fully settled. At the moment, very extensive numerical computations seem to indicate that it's unstable at a very small Lyapunov exponent rate. Actually, I'm not very sure how this competes with Sun's lifetime. But anyway, we have nothing to worry about. We have other things to worry about at this point. So Poincare was the first to point this out, but then afterwards there were seminal works by several other people. To just give an idea of, since I mentioned the two-body problem, the kind of things that arise, maybe I should introduce the notions of integrability. According to, so what is commonly referred to as integrability of Arnold and Liouville, we formulated this condition that a system of this kind is said to be integrable if there exists d constants of motion. Let's just call them f. So maybe fj. All the q's and all the p's put together. So they are constants of motion, meaning that their derivative does not change with time. So derivative with respect to time is 0. As you know, the derivative, so as of the moment, please notice that I've written a Hamiltonian function as if it does not depend on time t. We'll shortly time t, but right now it doesn't depend on time t. So this is equivalent to the condition that the Poisson bracket with the Hamiltonian vanishes. Of course, one constant is the Hamiltonian itself. The energy is constant without time explicitly put in there. So, but if there exists d of such constants of motion such that their mutual Poisson brackets also vanish. So H itself is one of the set of F. It's not d plus 1. One of the Fj is H itself. So if that is true, then according to these gentlemen, the motion is said to be integrable, and what it implies is that the motion is solvable in some sense. It can have no chaos. Motion is actually restricted to surfaces which are topologically like a torus in d dimensions. So the flow is like a torus in these. So basically, these Fj act like actions, and the conjugate variables are the angles, and these angles evolve in a trivial manner. They just basically are just rotations with a constant velocity of frequencies. So that's the, recall that a torus, a two-dimensional torus is just a square which is identified all these sides, the side identified with this side, the side identified with this side is topologically that. T1, what is T1? A torus in one dimension, just a circle, right? The circle, or we can't imagine anything higher, at least I can't, but it's a d-dimensional torus on which there are these d angles. Okay? There are these d angles, and the angles are evolving essentially like theta I is theta 0 plus omega I t. They're just constant rotations at constant velocity. So the motion is said to be integrable if there are these d constants of motion which are in evolution. If you cannot find these d constants of motion, or if there does not exist these d constants of motion, the system is said to be non-integrable. Yeah. Yes. Absolutely. It's a very good question. Absolutely. Yeah, yeah. So it's a very good question. Actually, if you see the book of probably, I think, Landau, unlike other Landau books, Classical Mechanics, small enough book, I think he points out that given any d degrees of freedom system, there exists these 2d minus 1 constants of motion. Because, after all, the orbit is one-dimensional. So there are these 2d dimensional space in which if you have one constant of motion, it will be reduced to a 2d minus 1 dimensional surface. Let's first start from that. So energy is a constant of motion, right? For whatever it may be. So a 2d dimensional phase space, it is not wandering all over 2d dimensional phase space. It is restricted to this 2d minus 1 dimensional energy shell. Okay, but it's not also wandering all over the energy shell. It's wandering over a subset of that. So 2d minus 2 and so on, because finally it's just wandering over itself, which is a curve. And it's a one-dimensional curve, so there has to be 2d minus 1 constants. As correctly pointed out, you could possibly take these constants as these, just this initial conditions. You could write down, qi of t as some function of all the initial conditions and time q01, whatever, pd, p0d, and time t, and so on. And then you could possibly invert these things. But notice two things. One is, first of all, these are time-dependent. In some sense, these are time-dependent functions. We are talking about these functions themselves will not depend on time. Their total derivative is explicit time dependence is not there. But actually, what is even more astonishing is that these 2d minus 1 dimensional constants of motion are by no means simple in the sense that they are, as surfaces, they are horrible surfaces. So they are completely non-analytic, and as if, so the motion occurs as if these constants don't exist. They don't respect, it doesn't look like it respects these constants of motion, just that the constants of motion are themselves very convoluted, that they are quite useless. So we will actually come back to this point, the point with, well, not exactly to this point, but I think a related point in quantum mechanics maybe. But notions of integrability and non-integrability have been discussed, dated for long and continue to be. But the difference between that kind of constant of motion is that these constants of motions are smooth functions on phase space. And they actually enable you to usefully constrain the orbits. I don't know whether I've completely convinced you, but you have to think about it. But it's a good point that there actually does exist 2D minus 1 constants, but you can't write them down in any, they're not useful in. Okay, so if these constants do not exist, then they are, the thing is said to be unintegrable. Okay, so chaos, or motion which is considered to be chaotic, usually occurs in systems, actually always occurs in systems which are non-integrable. So non-integrability is a basic thing. And why does a system, actually it's not very, today there is no algorithm even today, given a Hamiltonian, for us to find all these constants of motion. So sometimes it's not clear whether it exists or not. There are cases where people have thought some system was not integrable, but found it to be integrable, and vice versa. So usually these, the most simplest constants of motion are associated with symmetries. If you have rotational invariance, there'll be angular momentum conservation, translational invariance, momentum conservation, but we know only so much. And there can exist many more constants of motion, so you may not be able to always associate that with symmetries. If we are particularly interested in systems which do not have so many constants of motion, I guess I was coming to this also because of the two-body problem. So in the two-body problem, how many constants of motion exist is a very standard question at the, I don't know at what level. But you do know that there are several constants of motion. There is, of course, energy. There is total angular momentum. All components of angular momentum is conserved. What else is conserved? Yeah, there's a somewhat strange vector called the Runge-Lenz vector. The fact that there are actually far too many constants. If you count these, there will be more constants than 2D minus 1. So they are not all independent, first of all. So these are, I should have also written that they are independent. Of course, ones are not functions of others. So these are not always independent. These are not all independent, as you can see, Goldstein. But more importantly, these are sometimes referred to as superintegrable because there are more constants of motion than even D, or independent constants of motion than even D, which constrains the motion to not just lie on a torus of D dimensions, but actually on a torus of one dimension. I mean, in this case, it's just an orbit. The fact that the Earth is moving actually on an orbit, like not all central forces are constrained to move on a closed orbit. The fact that this is a closed orbit is because of the existence of so many constants of motion, additional symmetries are there. But once you put in a third object there, it destroys all of these, or rather, there is conservation of total angular momentum, etc., but the number of degrees of freedom is now increased by 3. And there's not enough constants of motion. And it does not, although there are more than energy, there are additional constants of motion, but not sufficient for the motion to be integrable, and it's a non-integrable system. So the solar system is a non-integrable example. Or if you look at the classical limits of any atom apart from the hydrogen atom, it's non-integrable. The helium atom is a three-body problem. You're asking whether those are in the integrable structure. No, usually these things are not discrete symmetries. They are continuous symmetries which will lead to these things. Yeah, I mean, parity and so on are discrete symmetries, charge conjugation, I would imagine. But yeah, right. Yeah. No, well, nobody has found additional constants, and yes, so nobody has found additional constants, but the question is, has anybody proven that there exists no other constants, right? I mean, that's what, yeah. So I think that way it's actually numerics. You can show that there exists, may not be entirely right here, but I think it is. I don't know whether, yeah, there's no, see, there are very few systems which are actually proven to be chaotic in that sense. We'll come across some of them. But otherwise, yes. The fact that there is not enough constants of motion combined with numerical studies of what's happening, we'll see like Poincare surfaces of section. You'll see orbits filling up volumes rather than, yeah. Okay. But I mean, I should say that there's a lot of work, mathematical work done with the so-called restricted two-body problem, wherein one object is very large and two small objects are moving in this field. There's actually a fair amount of mathematical work which I'm not familiar with. Okay, so what are the simplest systems that we can deal with? Obviously, D is one. D is one degree of freedom. There's only one Q and one P. Is this integrable or not? Are 1 degree of freedom systems integrable? Yeah? Yeah. Everybody agrees? All right. I guess the question is too simple for this audience. Yes, all right, because energy is conserved. Right. So energy is conserved, so there's D is one constant of motion, and for example, typical orbits might be like that, but they need not be like that. They can be scattering orbits and they can go off to infinity and so on. But if they are bounded orbits, they are bound to be cyclic, or there are some orbits which are bound but are not periodic, but typically they are periodic orbits. So what are so we need to go to D equals 2. In which case, we'll have Q1, Q2, P1, P2. And if there are not enough symmetries in the problem, you could have non-integrability. For example, let's take some standard examples from textbooks kind of things. So, particle in a cone, standard problem from textbooks. Is it integrable or not? Vertical cone, particle inside that. They would ask you to write down the Lagrangians and so on. Audience poll. Is that integrable? There are 2 degrees of freedom, first of all. You could take that as maybe the distance from this cone or something like. You could take cylindrical coordinates and take this thing and an angle, for instance. Yeah, what conservation? LZ, yeah. Yeah. So LZ and energy is conserved. 2 constants of motion, motion is integrable. How will you make this non-integrable? If we are interested in chaos, huh? No, we'll come to that. That's a good option. How do you make it non-integrable? Exactly. Your suggestion of making it time-dependent destroys the Hamiltonian as a constant of motion because the system is no more translation invariant in time. And his suggestion of tilting it also works. So you can either tilt it or shake it, do whatever you want with it. But if you tilt it, the motion on the cone becomes non-integrable. You can still, of course, write down the equations of motion. There's nothing strange about it. You can write down the potential energy, kinetic energy. Only thing, it'll look more uglier, but, well, that's life. And then you see that the system is non-integrable. So non-integrability is not something, in fact, integrability is something special, obviously. This corresponds to a vertical cone. If it is slightly away from that, it's non-integrable. In this case, it's clear from symmetries that it's non-integrable. You can go check it. It doesn't mean that all orbits in this are going to become chaotic. We'll come to what it means that something is non-integrable. But it means that the motion is not restricted to lie on these tori. And also the other possibility of making it time-dependent leads to non-integrability, but that's true even at this level, isn't it? Even at d equals 1 level, you could make the system time-dependent, and you would end up with, because the energy is no longer conserved, and so it's potentially a non-integrable system. So let's see whether this is alive. Oh, okay. All right, so this is sometimes referred to as 1.5 degrees of freedom systems, because an extended phase space of this, can I use that part of the board? So why is this no longer a good phase space when you have time dependence? Well, because if we were to start from some particular point, it could do something like that. It could flow and then it could cross itself at that point, because the no crossing, because the vector field, which is determining the Hamiltonian systems. So just look at this vector field, derivative h with respect to p. P dot is derivative h with respect to q. These are functions of the position, momentum, and time. So now it depends on time t, the field. So this q dot and p dot are just tangent to these things. That's how the flow is occurring here. That's the velocity. The velocity of the flow in phase space is q dot, p dot. Not to be confused with the velocity of the coordinates. The velocity in phase space is this q dot, p dot, and it's just tangent to this thing. So that is determined by this vector field. Whereas if it is time dependent, at any particular point, you can have two vector fields at two different times. And therefore, they can cross. And therefore, there's no sanctity of saying that, so this particular point is not unique. There can be crossings. So to avoid that, you might extend this phase space, so to speak, putting time there. So once we lift this, because they only cross at different times, they cannot cross otherwise. So once you lift that, then you have this important part of what you might want to call a phase space, namely that there is no crossing, right? So it's a 3D, it's a three-dimensional phase space, if you wish. And since the dimensionality of phase space divided by 2 is usually the number of degrees of freedom, some people like to call it 1.5 degrees of freedom. But basically, it's a non-autonomous 1 degree of freedom system. And that's a generic kind of Hamiltonian you might have. And yeah. Which trajectory is not closed? Yeah, it need not be closed at all. No. You mean periodic? Yeah, it can be. Arbitrary means you mean it won't cross and it can. Of course, yeah. Yeah. Why not? But I'm saying that it can cross. Need not cross all the time, but yeah, it will typically cross. I'll show you examples. On the curvature, why the curvature? Integrability will depend on whether there exists another constant, there exists a constant of motion. There could exist another constant of motion. I mean, one is not saying that because the h is not a constant of motion, but maybe there exists some other function which is a constant of motion. If you find that, then it's integrable, although it's time dependent. Is that clear? It need not be the Hamiltonian. Okay, so one very important class of problems which have been studied for a long time is when this function g, which is giving the time dependence here like this, is something which is periodic in time. So let's say that it's a periodic in time with period t, then important simplifications occur. So as an illustration, let's be concrete. Let's take some examples. Right? Let's take a harmonic oscillator, which we're all familiar with. And so we write this Hamiltonian, mass is 1, but here is a parametrically forced. So the frequency is changing with time in this manner. So if epsilon is 0, it's an unforced harmonic oscillator with a frequency square root of g0. And if epsilon is non-zero, it's parametrically forced. And then we'll compare it with a parametrically forced pendulum. Okay, so maybe the length of the pendulum is changing with time. You're oscillating pendulum or something like that. So that's the thing. So it has been arranged so that for small q, 1 minus cos q is just half q squared. So for small q, it looks like these two. So these two systems are identical for small oscillations about q equals 0. Equations of motion are simple. They're the same, derivable, but now they depend on this time t. And then we have to integrate these equations, and let's look at some orbits. So we see these orbits, and this is harmonic oscillator, this is the pendulum, and we choose the same initial condition in both of these. Okay, so same initial condition, you see that this is for the case when there is no forcing, so epsilon is 0, and that's the ellipse which we all know exists for the harmonic oscillator, the phase space of the harmonic oscillator. And this is the phase space of a pendulum. So one of the very first exercises, the most elementary one, is to draw the phase space of the simple pendulum. So this is the simple pendulum. Why is this thing very unellipse-like? Yeah. Yeah, so it's actually very close to the equilibrium point here of pi. So here is plotted the angle. Okay, that's q is angle. So the unstable equilibrium point is at pi 3.14. This is chosen at 3, so it's very close to that. It's a large period oscillation. Oh, it's actually very close to that. So it's a rigid thing out there. So it's coming down, it's going up, and so on. Okay, back and forth. So it's a high energy oscillation, and we see the same initial condition, but change the parameter epsilon. For the harmonic oscillator, you have this. So there are no crossings. You're seeing the crossings in phase space. And, but it looks like a nice set of, it's restricted to this area nevertheless. Whereas the pendulum develops orbits which are, they are looking very messy. There is this predominance of orbits that are crossing each other, apparently stochastically or looking a bit messy. That's all I can say at this point. And this is at an even larger value of epsilon. So there's a large forcing here. This region has become larger, and this region also has become larger. But these motions are clearly qualitatively different from these kind of motions. Okay, so this is at an even larger. So this is epsilon 0, 2, 5, and 10. Okay, this is a much larger thing. And then you can see that these are orbits which are actually going all over they include rotational orbits and so on. Okay. Yeah. Well, it's a good question. Go and figure it out. It just so happens that for this particular initial condition, that's for the times that I have integrated, it is like that. I mean, the symmetry need not be preserved. So I don't know if that's the question, but if the question is a more detailed, why in this particular epsilon this thing is doing that, I don't know. But if it's a question of why there is no symmetry here, there need not be symmetry. I mean, the Hamiltonian can have a symmetry, but the orbit equations of motion, or the orbits need not have that symmetry of motion. Yeah, it can have something which is opposite, exactly. Yeah, exactly. Good, yeah. Yeah. This particular orbit preserves symmetry here. Well, that again is a good question which I haven't explored. Okay, so I mean, it looks like to me that it's possible that there is actually a symmetry breaking in this case, which is not here in the individual orbits. Yeah, yeah, yeah. Of course, there's nonlinearity, but in terms of symmetry, please note that they're the same. Okay, both of them have the same symmetry properties. There's q squared, there's cos q. There's nothing which is different symmetry-wise. Both have a reflection of parity symmetry. That's about it. But of course, there exists an additional constant of motion in that case. We'll come to that. Okay, but I haven't done a detailed study of this. But I mean, I like your questions. You should explore. All right. So why does this motion of this look? So first of all, one of the important things is that this is not a good idea. It's not a good idea to look at things in phase space because this is just one orbit, and I would like to explore other orbits. And if I put on top of this another orbit and another orbit, another orbit, it's going to be a god-awful mess. So, and especially here. So this is not a good idea. What is a good idea? Good idea is to make use of the fact that the system is actually periodic in time. In the sense that the system is not periodic, the forcing is periodic in time. So the Hamiltonian itself is periodic in time with some period t. So if suppose we denote, so what actually fails in this? So let's denote by ft the map which will take an initial point qp and give you the position and momentum at a later time. Okay, so this is the map. It's a map or a function which will, this is basically what you would have if you integrate those equations of motions. It's an integral form of those differential equations. It gives you that, right? You understand what ft is. Now, if the system was autonomous, then if we evolve for a time t1, we have this map ft1, and then we evolve it for another time t2, ft2. What would this be equal to? This would be equal to just evolving it for the time t1 plus t2. Okay, it has this so-called group. It's a semi sort of a groupish property, right? I mean, we're not going into the negative time, but in this case, you can also go negative time. So it's just a abelian group structure. However, if the Hamiltonian is dependent on time, this is no longer true. Why is that? So if it's dependent on time, it's no longer true. Because the evolution law, F, which you have got over a time t1, is not, so you have just evolved this over from some, let's say, 0 time to time t1. You have got this map ft, ft1. And then you want to evolve it over another time t2. Okay. So, but the equations of motion, which are the conditions, the Hamiltonian, which is there here, or the Hamiltonian to be specific, the Hamiltonian which is there here is not the Hamiltonian which is there here. And therefore, this is not your evolution. This is not just f of t2. This is actually f of t2 minus t1 starting from here. So actually, it's a different f altogether. So we cannot write this. In other words, actually for this, in the case of when there is time dependence, we need to specify this, let's say a base point. Where you're starting from is also important. Not just how much time is elapsed, but where you start from. So suppose you start from 0 and you evolve for t1, you get this map. If you start from t1 and you evolve for a time t2 minus t1, you'll get this map. Actually, in what I've done there, I'm evolving. Oh, so this is t2 in this case. So that's the interval. So let me just keep that as an interval, t2. Okay, so but this is not equal to f0 t2 if there is time dependence. However, there is a particular simplification because of the fact that it's a periodic evolution in time. What is true is f0 t is equal to ft t. That is, if the base point is after a time which is the time period of the Hamiltonian, then the system is basically back to, the equations of motion are basically back to what it was before. And therefore, when you evolve it, it has to be the same map. So this is the crucial point that you need to either accept, understand, or whatever, right? Yeah. Yeah, this is some initial point, yeah. And if you wish, we could put a 0 here also based on our discussion there. Yeah. No. Floquet was not a quantum guy. Floquet just did linear differential equations with coefficients that are periodic. This is exactly a Floquet system. Yeah. So, but Floquet is usually linear systems. This is, but yeah, I mean, no. Generally, these are called Floquet systems as well. Floquet analysis is typically for linear. Okay, so but these are also just called. So what we need to do is not worry about. So I'm just talking about this thing here. So what we need to do in this case is to integrate basically over one time period. Wherever you start, it makes sense to integrate over one time period, and then we can iterate this. Namely, if you compound this with another time period, this will be the same as starting from that. Actually, this will be 0 to t and t to, let's say, 2t. So these are now, this is absolute time t. So you're starting from t and evolving to 2t. This is same as starting from 0 and going to 2t. Okay, this is true. So it means that we don't monitor this Q and P at all times, but only monitor it at times which are multiples of the period of the forcing. That is capital T. Okay, so there could be several typos. Please point them out, but not here. Yeah. Yeah, it's the same. I've just put. Oh, I've put that. Yeah. This is also true. Yeah, that's not a typo. I mean, it's also true. I mean, it just means that you can apply the same map because this is also the same as. Thanks for pointing that out. Actually, it's also the same as 0 to t. So it means that if you have a map which is, you have integrated it or till a time which is a period t, then you can just iterate that map, okay? Some of these things may be confusing, but the point is that you need to integrate over a time capital T. And that happens. So you don't look at the entire bit. If you were to look at just the time t, then the harmonic oscillator now looks like this. So now it's a discrete set of points, and this is the pendulum. It looks like this. So it's a very messy set of points, looking kind of random, but here it's lying on a curve. And this is for another set of, so there's the same set of initial conditions which I showed. In both these cases, epsilon is 1 and G0 is 3. 400 iterations. Yeah. More initial conditions, right. So in both of these cases, we have a large forcing. Epsilon is 10. This is a harmonic oscillator. It's just one orbit, which is shown. This is the pendulum. And this is many orbits. So the fact that you cannot see many orbits in the same thing is now overcome by looking at stroboscopic maps rather than flows. Okay? So, but now you can see the structure which is evolving for the pendulum. And this is a typical structure for 1.5 degrees of freedom or 2 degrees of freedom Hamiltonian systems. So you have orbits which are starting from here, which would explore this region, which is just, it doesn't follow any, so it seems to fill a region which is not one-dimensional. It's actually a two-dimensional region it seems to fill. Whereas if you start from here, it seems to go on here. Just on this orbit. Maybe it can go till here. It can cross from here to here, and then it can go back there, and so on and so forth. So the point is that depending on the initial condition, you could have motions which look stochastic or ergodic or chaotic, and those which look regular, depending on the initial conditions which you start from. This is the case of the pendulum. The same forcing and amplitude for the harmonic oscillator gives rise to these ellipses. So that's the difference between a forced harmonic oscillator and a forced pendulum, and this is where the nonlinearity plays this crucial role of leading to chaos. Okay. Why is the harmonic oscillator simple? And in fact, whatever may be your forcing, it need not be this cos 2 pi t. You can take any periodic forcing, you will get ellipses, or you will also get hyperbolae. It could be unstable and go away. So that, as was mentioned, is a consequence of Floquet. I probably will leave it as an exercise to you, but I have. So this notes has several exercises, so you can go through them. So it's quite simple to argue why in a harmonic oscillator, whatever may be the kind of forcing you might have, the stroboscopic map is an ellipse, or it could be, as I said, an hyperbola, or maybe a parabola, but nothing more complicated than that. Yeah. First map. This one? Wait, this is not a map, this is a flow. Yeah. So this is for all time. We just integrate, you practically, you use a computer, right? You integrate the equations of motion, and you're just plotting it at all times. Okay. Now, you have a period of the forcing. In fact, I've taken the period as 1. It's 2 pi t. So on your computer, you would only take that q and p which is separated by 1 time unit of 1. So let's say that you start with some initial position p0, 0. You integrate this. It's a continuous differential equation, as you can integrate this for all time, but you don't bother about it. You just take time 1, p1, and then time 2, p2. This is actually 2. It's not your second iteration in some routine, numerical routine. So at every time, so q at t equals n times the time period, monitor. So that is this n. So basically what we are writing is this is being plotted, qn pn. qn pn is simply the position and momentum at every period of the forcing. Is that clear? Is that clear to everyone? How are you getting that? Yeah. let's look at this. Is that a problem? So what you're asking is, if we were to start from here, would it become stable? Or if we start from here, would it become unstable? No. So if you start from here, forever it is constrained to lie on this. If you start on this, it's forever constrained to lie on this. It's either, it has to make a choice. Absolutely. Yeah. All these are, I mean, there could be some intermittent chaos, there could be all that kind of stuff. Right. So even in these systems, there can be, for example, if you have an orbit which is coming very close to, let's say, this orbit here. Okay. So it may look like it is. These have important effects in the dynamics. Those are all details. There'll be sticky dynamics with the existence of regular region. So in fact, I should say that the border between the regular and the chaotic is not so simple. It's not like, it's worse than Pakistan-India border. I mean, it's much worse. It's a fractal. It's everything. It's not quite well. Okay. So, and even within this, what you might think region of sanity or regularity, there would be chaos. If you look closely within this, there would be chaos in this neighborhood. If you look even more closely within that chaos, there would be regular regions ad infinitum. Okay, any other questions? That's only the first row that seems to be asking questions. Maybe we should have a rule. First row asks questions only for the first 5 minutes. And second row. Well, second row also there was some questions. Thanks. All right, so anyway, I wouldn't hassle you. So there are some, how would one consider this? I've actually given an exercise. I don't think I have time to go through that, but since it's an exercise, you can do this. Here is, if you did not understand what I said so far, it's perfectly fine in terms of constructing a stroboscopic map, but here is an exercise which should help you do that. Here is a forcing which is simple. It's not a cosine. It's just, it's on or off. So what you have is what is called a Jekyll and Hyde Hamiltonian, namely stable for, let's say that you have a harmonic oscillator which has got this potential q squared by 2 for some time. And after that time switches to minus q squared by 2. Stable, unstable, then goes back to stable, switches back and forth with a period time t. Okay? Would the motion be, eventually, would the motion be periodic? I mean, stable or unstable? That's the question. Obviously, it would depend on this time t as well as on the frequency of this original Hamiltonian, maybe we'll put here. So that determines one time scale, and there is this other time scale of switching. But what do you think, without solving anything, if the switching was very fast, would it be stable or unstable? How many people say stable? Switching is very fast. That's what I mean by very fast. That means that it's the time period between switching is much smaller than 2 pi by omega. Right? Yeah. Okay. Those who voted 1, so it basically is stable. Okay. So those who did not vote did not win. So you should vote. Okay. So basically, if you do it really fast, it means that it's almost there. I mean, it's like the it's completely stable. I remember from, that's why I don't finish on time. There's still half an hour, because I have to tell you about a video I saw in my childhood about Muhammad Ali. Muhammad Ali was this great boxer, and I think he was in India once and they interviewed him. And the interviewer said, Ali, demonstrate how fast you can box. So Ali said, hold up your hand. And this guy held up his hand rather bravely. And Ali said, like this. Said, see, I'm boxing. So he was boxing, according to him, so fast, you can't see it, right? So it's similar. So if you really do it fast, it's like you're doing nothing. Okay, it's not like you're not doing nothing, but it still remains stable. But it's an interesting problem for which you can write down exactly the stroboscopic map, okay? And so what do I mean by you can write down exactly the stroboscopic map? It means that you can write analytically what this function f is, which I said, and it is of the following form: q n plus 1 p n plus 1 is a matrix A, B, C, D times q of n, p of n. So that's the stroboscopic condition. By this plus 1, I mean plus capital time t. Okay, the next iteration. Is that clear? So q of n plus 1 is just a times qn plus b times pn, where this a, b, c, d are constants, independent of q and p, also independent of n. So you see, although there was a time dependence, because of the periodic time dependence, this has essentially become also some kind of a non-time dependent system. So it's an autonomous map. So this you would call a map, okay, because it's just discrete in time system. So how would one find the stability or lack of stability of such a system given this? It's very simple, because this is a linear map. So Qn, Pn is this matrix, let's just call it M, raised to the power of n, Q0, P0. Right? So the dynamics depends completely on how this matrix is powers are taken. And how do you find out if this is stable or not? Depends only on how this matrix power behaves. And you know how matrix powers behave, or how matrix powers are calculated using just diagonalization. So if P is a bunch of eigenvectors of this and lambda are the eigenvalues, then that holds. And all the time dependence is in the eigenvalues raised to the power n, right? So there are two eigenvalues in this case. It's a 2 by 2 matrix, lambda 1, lambda 2. And from general fact that it's a Hamiltonian system that we are getting this map, there is a further constraint. The constraint is that the determinant of M is 1. This comes from the area preserving property of the map. And in a sense, it has to do with Liouville's theorem that areas are preserved in phase space. So determinant of M is 1 implies that lambda 1, lambda 2 is 1. So you know that then only lambda 1 plus lambda 2 is important. I mean, what I mean is that for a 2 by 2 matrix, the determinant is determinant and trace are the only two invariants that matter. And because you can find the eigenvalues based on that formula then. The determinant is 1, these are the eigenvalues. So when would this be stable or unstable depends only on this trace of this matrix. And if the trace of this matrix has a modulus greater than 2, then it implies that this lambda 1 and lambda 2 are both real. And if they are both real numbers, they have to be, one has to be greater than 1 and other has to be less than 1 to compensate for this fact. Both cannot be less than 1, both cannot be greater than 1. Okay? You can deal with negative numbers, okay, but in the same way. But this has got to be true. Always there has to be an eigenvalue whose modulus is greater than 1. But if there's a modulus which is greater than 1, that eigenvalue, this lambda to the power of n, increases exponentially and is unstable. Therefore, the condition of this is unstable. And if it's less than 2, stable. Because both the eigenvalues will then be complex conjugates of each other. And it'll be just rotations. And so you can, based on this, figure out whether this Jekyll and Hyde Hamiltonian, which is half the time stable, half the time unstable, with a switching time t, whether it's a stable system or not. Yes? Very good, yeah. So equality is a marginal case, of course, so I always avoid it. But equality means neutral, so it's like free motion. It's but also a very important point, actually, because equality means that So in terms of equilibrium points, this means that there is one equilibrium point. There's always an equilibrium point, which means things are not changing with time. What is the equilibrium point for this map? A trivial equilibrium point. 0, 0. And is actually the only equilibrium point. That means only thing which does not change with time. That's at 0, 0. 0 position, 0 momentum. And if it is modulus is less than 2, then the orbits will be a set collection of points like what we saw in the harmonic oscillator. So it's an elliptic point, right? And if it is greater than that, it will be like a hyperbola. So there'll be this kind of behavior, and it's unstable. So the intermediate point is one of a bifurcation. So trace m equals 2 is a condition when the nature of this fixed point is changing. In this case, it's not really a bifurcation in the sense that you don't have new periodic orbits coming, but typically in a nonlinear situation, it's a condition for bifurcations. The nature of the periodic orbit is changing qualitatively at that point. But you can play around with this at exactly this. In this case, there's no real bifurcation because there's no other periodic orbit, as I said. That's small, I think. Okay. All right, so nonlinear maps. So this was actually an example of what you might call a linear map because of the obvious reasons. It's linear. So nonlinear maps in 2 dimensions. So 2 dimensions, there's only Q and P that I'm talking about. So this is the general thing. So at Qn and Pn is determined by 2 functions that need not be linear functions like AQ plus BP. So they're arbitrary functions. But they satisfy for Hamiltonian systems. If this map is coming from a Hamiltonian system, as I said, it has to follow this condition of determinant being equal to 1. If you calculate the Jacobian of this transformation, just think of it as a transformation. So there's a Jacobian of the transformation that can be calculated. Then the determinant of this Jacobian has to be 1. This follows from general considerations. And if you derive this from a Hamiltonian, you would find that it is 1 from, okay, if you find that it's not 1, it means you go back, check your calculations. Now, what happens? How do we make use of this to describe stability properties? If you were to start with some Q0, P0, and another nearby point, Q0 plus delta, Q0, P0 plus delta P. So we want to see how this small variation, delta Q0, delta P0 changes with time. So, but that's, how does it change after one step? After one step, we just have to multiply by the Jacobian. It's just a Taylor series expansion to get delta Q1 and delta P1. How these orbits are differing after one iteration is by multiplication by this Jacobian matrix. Is that clear? I mean, we have Q1, Q of n. Let's see, how would I write that? Qn Pn. Okay, so I wrote like Qn plus 1 equals F1 Qn Pn. So simply delta Qn plus 1 is derivative F1 with respect to Qn, delta Qn, Qn. Delta Pn, delta Pn. And similarly for the other one. So if you write this as a matrix equation, delta Pn plus 1 is another one, then you would write this as this Jacobian matrix of these partial derivatives multiplied by delta Qn, delta Q, delta Pn. This Jacobian evaluated at Qn Pn is delta Qn plus 1 delta Pn. Okay, so the Jacobian is just telling you how locally things are being extended. So this Jacobian depends because they are these derivatives of these functions which themselves could depend in general on these, on where you're taking the derivative. So this Jacobian depends on this point Q0, P0. And in the next iterate, it's gone to Q1, P1, and so on. So you have a product of Jacobians which connect these, this initial displacement to the final displacement. So you have this product of these 2 by 2 matrices, and if we call this product Jn, that the properties of Jn completely determine what are how unstable or stable the motion is. And so suppose you were to take the length of this vector, the difference between these two orbits. If you were to look at the distance between those two orbits, basically it is governed by the matrix, which is the transpose of J times J. And therefore, the eigenvalues of this matrix Jn transpose J is telling you something about the stability of that particular orbit which you started out from, that central orbit. So if those eigenvalues, and this is a positive matrix, it's a positive matrix because you've taken a matrix, taken its transpose and multiplied by itself. It's a real matrix, it's a positive symmetric matrix, and it's got positive eigenvalues. And if those eigenvalues are denoted as mu I n, so this depends on time n here. Okay? If they are exponentially growing, these eigenvalues exponentially growing, then it is unstable. So you would take the logarithm of that and divide by 2n because you are taking essentially the distance squared. So you just want to see how the distance is changing. So you would take a square root of that. So that's why this 2 is there. And then you take the limit as n goes to infinity. Long time, how this orbit is separating. That is a number which depends on Q0, P0, your initial point. That determines your orbit and is called the Lyapunov exponent of that particular orbit. So the Lyapunov exponent of the particular orbit tells you how nearby orbits are separating in time. So that's the usual picture. So here we have delta Q0, delta P0, at some later time, delta Qn, delta Pn, and this distance here is growing as e to the lambda n. Is growing as e to the lambda n, and if lambda is positive, it's actually growing. If lambda is negative, it's shrinking, and if it is 0, it's 0. So there is 0 Lyapunov exponents. Nothing happens to these things. They're not either separating or coming together. Okay, so sorry, excuse me. So these numbers are a very important part of measuring stability of orbits, and I point out that in the case of area preserving maps, thanks to this condition that lambda 1, lambda 2, these eigenvalues of the Jacobians are equal to, the product is equal to 1, the Lyapunov exponents always come with a positive and negative sign. The sum of the Lyapunov exponents is 0. And this is true in general for any higher dimensional system. And again, it's an exercise how in higher dimensional systems, which is you generalize the area preserving maps to symplectic maps. And you know what symplectic transformations are from, or canonical transformations are from course in classical mechanics, then you can prove that, in fact, this implies that the Lyapunov exponents, there'll be as many of them as the dimension of your phase space, because there are as many directions in phase space, independent directions as the dimension. All of them sum to 0. So there can be either, if there is one which is positive and leading to instability, there is one which is also negative and is pushing them together. And this is a property which is coming from Hamiltonian flow being the Liouville condition of preservation of volume. Mm-hmm. Yeah. Yeah, we will come to kneading dough. We'll come to kneading dough. It's a very important example, actually. Kneading dough. but I'm not sure. I have 14 minutes according to the clock. Okay, so I'm sorry if I'm going a little bit fast here, but it's all there in black and white for you to take your leisure and read it. But it's basically what I'm saying is that we have to measure the stability of orbits. And how do we measure the stability of orbits? We look in its neighborhood. The neighborhood is determined, the neighborhood determines the Jacobian, which is telling you how it is spreading at that particular point. When it has gone from one point to another, the Jacobian there then determines how it's spreading. So it's a product of all these Jacobians, which is telling you how the orbit is eventually stable or unstable. Okay, so, and from that you can derive these Lyapunov exponents, which are a quantitative way of saying whether something is stable or unstable. Okay, so I'm going to talk about some. So I talked about this Jekyll and Hyde thing where you write down easily the map, but that's a linear map. Nonlinear systems are what we are interested in. That's what leads to chaos and so on. It's difficult to integrate and write down explicit forms of these things, except for a class of systems which have been studied almost since the beginning of the 80s, actually late 70s, I would say, is these so-called kick systems. So rather than turning it, so you just turn on and off a particular force or potential. So you're just kicking like the football is being kicked around at periodic intervals when it meets a player, but otherwise it's free. So if you consider this kind of a Hamiltonian, this particular forcing function is just a strain of delta functions, then it's rather simple to integrate the equations in between the kicks because it's just a free motion. And then at a kick, it's a delta function. So what happens, it's an impulse and the position is frozen and the momentum is changed. So in between the kicks, the momentum is frozen and the position is just changing trivially. And at a kick, the position is fixed and the momentum is changing according to the potential that you're applying. So this is the kick systems, and that leads to a stroboscopic map, which is explicitly writable, and therefore we don't need the Ranjekuta method. On your computer, you can just write this down in a simple two-line code. So Qn plus 1 is Qn plus the time between the kicks and a function of Pn, the derivative of that function, which is there in the Hamiltonian. And this is actually the free motion part, and this is the impulse. So Pn plus 1 is Pn, and then this is the force. This is the impulsive force. So, but it's important that this is the impulsive force at time Qn plus 1. It's not a typo. This is Qn Pn, this is Qn plus 1. Only if that's the case, and that's how it comes out in your derivation, it's an area preserving map. Okay, so you can prove that it's an area preserving map. And we'll take some special cases. A case when the kicking potential is a harmonic potential. A harmonic potential leads to a linear map, and which we already know how to solve. So this is another example of a linear map like the Jekyll and Hyde map. So you should actually compare it. So here also there is a forcing, there is a natural frequency, and you can figure out when it is stable and when it is unstable. And there are very interesting differences between this and the Jekyll and Hyde case. You should look at what happens. And this is one of the most important maps is the kick pendulum. So this pendulum, but now that's the potential is cos q, but it's now kick. And then you get this stroboscopic map. So that's Qn plus 1 is Qn plus Pn. I put a modulo 1 because it's an angle now. So it's modulo is 1. I've chosen the rotation to be 1, perimeter to be 1. And Pn plus 1 is Pn minus this constant k by 2 pi sine. So this is the nonlinearity is coming due to this function here. So this is a famous standard map, sometimes called the Chirikov map, the Taylor-Chirikov map, and so on. So this is a one parameter map, and there are other maps which I will show. There are also integrable maps, but I won't go into that. But here is an example of what happens in standard pictures of what happens in the standard map. You will see that in many books. So what is plotted here? Maybe I should use. This particular map has been realized using cold atoms in a different setting. This is 1995. So there are important phenomenology of this. We haven't come to the quantum case, so you're way ahead of me. But in the quantum, there are important differences. I still haven't come to that. Yeah, but yeah, this has been realized experimentally. The quantum version of it as well. Okay, so what's plotted is simply Q versus P. So the map is Qn plus 1, Qn plus Pn, modulo 1. If it is more than 1, you subtract an integer. Less than 1, you add, and less than 0, add an integer so that it's lying between 0 and 1. And Pn plus 1 is Pn minus constant sine 2 pi Qn plus 1. But I've also put a modulo 1 here. You could put a modulo 1 or not put a modulo 1. If you put a modulo 1, you get a map on a torus, on a 2 torus, because it's now periodic with period 1 on both sides. If you don't, then you get a map on a cylinder, because the momentum can go from minus infinity to infinity. Angle is 0 to 2 pi. But both of them are related by a symmetry. So it's sufficient for you to look at what happens in a torus. If you look at what happens in a torus, many copies of it make up what's happening in a cylinder. Exercise. But anyway, so if you were to just look at this as a map on the torus to itself, then for small k values, you will get a map which is looking like this, which is looking almost like the phase space of a pendulum. Okay, here we have these separatrices, we have these elliptic fixed points, we have these rotational orbits. But as k is increased, actually I think this is k is 0.3. So I would have the values here, 0.1, 0.5. Okay, so this is 0.1, this is 0.5. You see that there are these other so-called resonances which show up. So this is the iteration of many different initial conditions. Okay, and this is at value of 1. You have now development of chaos, like what we saw in the other case of the pendulum, parametrically forced pendulum. We see the similar kind of phase spaces here, but there are still these mixed things. So you have regular and you have chaotic ones. And then at 2, you have a phase space which is largely chaotic, but you have these regular things. And 5 and 7. Okay, so I can't seem to scroll that, but basically at this point it's fully chaotic. Okay, so this is a typical behavior of a 2 degrees of 1.5 degree of freedom nonlinear map, or a 2 degree of freedom Hamiltonian system. Yeah. Sorry, can you please? Anti-commutation algebra. What's that? The Poisson bracket, you mean? This is classical. We haven't gone to any quantum yet. They are completely classical, and yeah, of course, they are conjugate variables. How do you check whether it satisfies algebra? I don't know. You may check whether the area is preserved. Numerically, you can check to see whether it's really a Hamiltonian evolution that way. But otherwise, I don't know how to check. Think about it. Yeah. You didn't miss. I haven't come to that. I'm sorry, yes. But if I define chaos to you right now, it might also not make sense. So I need to build up the story a bit. Okay, very good. So let's see. Intuitively, what do I mean? Actually, I should have said that. What an idiot. I should have said that. So let me go back, way back. I should have said that here, thanks. I go back to my earlier example. Here I haven't. See, these two, we go back to the parametrically forced oscillator. So this is an orbit which is starting off at Q0 is 3, P0 is 0, okay? And it does this for the pendulum, it does this for the harmonic oscillator. And this is for an initial condition where the same Q, but P0 is slightly different from 0, 10 to the minus 3. It's slightly off. And the story goes that this is pretty much the same as this. The harmonic oscillator looks pretty much the same. Whereas the pendulum, there is this quite different from this. So this is the sensitive dependence on initial condition, one of the hallmarks of chaos. Okay, so that's why I'm talking about also stability. The fact that you have something which is unstable implies that initially close by orbits become totally different later on. There are other characterizations of chaos which I'll come to later, but this is an important point which I seem to have completely missed about sensitive dependence on initial conditions. Okay, that's what I mean by chaos. Thanks. Order in what? An average would bring in some kind of, I mean, if there is ergodicity, an average would bring in some kind of uniformity, or, like a lot of orbits will have the same average behavior, that kind of thing. But you're not going to see miraculously stability out of instability. Yeah, but I should also say the following. We'll come to that, but I don't know whether we will. That chaos does not mean, like, okay, let's go back to these kind of pictures. They seem to give us a sense that, so this is a single orbit. This could be a single orbit which is doing that. Maybe I go to some other cases. Okay, so there is, for example, here. So I illustrate this in the case of billiards in this case, okay? So let's just go forward a little bit. A billiard is a different kind of a system, but also it also has similar characteristics as what I've been talking about. It's just a free particle. We have all studied particle in a box. This is particle in a two-dimensional box, two-dimensional enclosure, and it's just specularly reflecting. So angle of incidence equals reflection. And this is a circular billiard. One orbit in that is shown here. Is just reflecting off that. And this is for a squared billiard. Is reflecting off the walls, and it's doing that. This is an elliptic billiard, and it's doing this. These are all cases of an integrable system because 2 degrees of freedom, angular momentum is conserved. Here, that both the components of the modulus of the velocity are conserved. Vx and Vy velocities, the modulus is conserved. And in the ellipse, although there is no circular symmetry, it's an interesting fact that there is a conservation of angular momentum. A product of the angular momentum about the two foci is conserved. Ellipse is a very beautiful example of that, and it's something which you can also do as an exercise, is to prove that an elliptic billiard is integrable by showing that the product of the angular momentum about the two foci is constant. And therefore, these are all integrable. But that's about it. You take any other shape, you're going to end up in some form of chaos or non-integrability. Here is an example of taking the square, cutting off a circle at the center of it. It's called a Sinai billiard, after Yaji Sinai, who proved mathematically that this is completely chaotic. So here is one orbit which is doing this. Now you see there's a clash of symmetry in this. So that's breaking the overall symmetry in this problem. This is completely chaotic system. Here is a famous Bunimovich or stadium billiard. Oh yeah. Okay, thanks. So It's 11. And I'll finish in 5 minutes. Okay? I think I started 5 minutes late. Just give me 5 minutes. So this is a single trajectory in the stadium billiard, which consists of just straight line segments and semicircular arcs here. So, okay? And that's a single segment. It's also proved to be a completely chaotic system. There's also another example of a completely chaotic system, which is a distortion of the circle, the cardioid shape. It's a cardioid billiard. So in all of these things, there is this sensitive dependence on initial conditions that I was talking about. So the cardioid shape is this. Yeah, so I've stolen these pictures from a particular place. Yeah. Yeah. Yes, naturally. I mean, if you were to somehow distort this so that it goes to that, it will smoothly go from a chaotic to a non-chaotic system. Similarly, a cardioid to this, for example, here is this thing. This is an intermediate. So when epsilon is 1, it's a cardioid. If epsilon is 0, it's a circle. So you can go from here to here. There would be intermediate dynamics as you're doing this. Yeah. Motion is symmetric. You mean like a circle? You mean yeah, right? Yes. I mean, you mean that if you're, I mean, I don't know if you're talking about small distortions of this or any of these shapes. Right, yeah. So I will take the circular orbit. So this particular map is for epsilon is 0.3. So this particular thing looks almost like a circle to you, but it's actually not. It's a distortion of this shape. 1 plus 0.3 cos phi in polar coordinates. So it looks like almost like a circle, and it's got an interesting thing, which is like the standard map, which I showed you, in the sense that now this is also a map which you're deriving from this billiard, although it's not a time-dependent system. So this is called a Poincare surface of section. I'll just tell you in a minute how you're deriving it. Maybe I'll tell you right now how you're deriving it. So you have this motion on this enclosure. So you have this ball which is going there, bouncing, coming back. Then there's this normal, I don't know, does something like that, right? And then it's going on doing this. How does one construct this kind of, how does one study this kind of dynamics? It's now in a 4-dimensional phase space with energy conserved as 3 dimensions. You can put what's called a section and make it into a 2-dimensional map. Okay, I should have come to all of that. But basically, you can plot the following quantities. On this axis, you can start from some point and measure arcs, okay, distance along that. So where it is bouncing off, we'll measure that. We'll measure this as, let's say, S0. And the other is, let's say that we construct this normal, and the velocity is going to be, the speed is going to be conserved because the reflection is elastic. So you could just take the cosine of this angle here. So that gives you the tangential velocity. So the tangential velocity you can plot here, phi n versus Sn. So the next thing here, you will get this to be your arc length S1, and this will be your cos phi 1. You should realize that these two are sufficient for you to completely determine the orbit. Suppose I tell you how it is coming in here and how it is, meaning this this particular angle, cos phi, and where it is going to impact it, that completely determines uniquely the orbit. This is also a map because it's now discrete in time. It's now the time is between these bounces on the boundary. That's all that matters. Intermediate, it's just a free motion. So that's called the Poincare services section or a Birkhoff map. That's what you're seeing here. That's what is shown here. So this is this arc length, and that is the momentum along the tangential direction. And what you see is a region which can be called chaotic or ergodic, and regions that are regular. If you were to look at an orbit, for example, this central orbit here, this will go here. Actually, these 2 points are the same because this is the, this is this distance. So you're going either this way positive or this way negative, you will come to the same point. So it's actually a cylindrical phase space here. So this point is the same as this. This is a different point. So you get this orbit here, it's a periodic orbit which just keeps bouncing back and forth, back and forth. So that's this. It goes, in the case of map, it will go here, 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 bounce back and forth. The neighborhood of this set of points, although you see it like a curve, it's actually just a set of points. Remember, it's a map. If you look at that, how it looks in the billiard, it looks like this. So it's also stable. It looks like this. And similarly, here is a more complicated periodic orbit. It's a triangle. So it goes from here to here to here to here and back and forth. So that's a periodic orbit. It's bouncing 3 times on the thing. And a neighborhood of that which is stable looks like this, in this neighborhood. But if you take a point in this blue part of it, which is chaotic, it actually fills up, it seems to fill up this billiard almost uniformly. We cannot say that it's uniform, but it seems to fill it up in an ergodic manner. So this is a single orbit and it does that. So you will have instability here. Initially, nearby points here will be completely uncorrelated after some time, whereas here there is stability. Is that? So, yeah. These patches here, you mean? They're also stable orbits here. They're not just shown. So if you go in and start an initial condition with that point, my computer says shut up. So, shut up. So. Yeah, if you start from there, it's also a periodic islands. Yeah, they're all regular orbits. They're all like resonances like these. I wrote resonances like. What is this x-axis is what you're asking? So it's the distance along the perimeter. So I'm looking at only the bounces when it's bouncing on the billiard wall, right? So we can measure how far away it is from some fixed point. It's an arc length. So it's just in this particular case, it's going from -4 to 4. Is you can start from, let's say here, characterize this as +4 and this as -4. Okay, so this is an example of a small distortion, but however, this you might think is small. It looks almost like that, but it's got a very large volume of chaotic region. Okay, so there's another example which I have here of this. This is not a time-dependent system. These are autonomous flows which lead to this. Another example of a 2-degree of freedom enharmonic oscillator, which also has a similar structure. So you can see these are the surfaces section for this oscillator. Maybe I'll come to this when I'm doing quantum in more detail. But okay, so our next agenda is to look more closely at Poincare recurrence, ergodicity, mixing, and I will define chaos for you tomorrow. I will put up these notes and maybe we meet in the afternoon during the tutorials and discuss more. Thanks.
Maybe we leave the questions for the tutorial, and since it's slightly late, so we break for tea and meet at 11:30.